So last week I was watching the Joe Rogan Experience and his podcast. He had Neil deGrasse Tyson on, a guy I really like a lot, fascinating to listen to, very knowledgeable. They were talking about various science subjects. And I really like the podcast. If you haven't checked it out, you should check it out sometime because he has these people on. He does a really good job with his interviews. But anyway, they were talking about quantum mechanics, and Tyson was trying to explain an aspect of quantum mechanics. And he got it wrong, I think. So let's check out the clip, and then we'll discuss.
While we're on this subject of subatomic particles and weirdness, I wanted, if you could, illuminate this often misused explanation for the observer effect. Because, you know, the particles, waves, and you watch them, observe them, and it changes the reaction.
It is heavily misunderstood.
It's misunderstood because people want to attribute it to magic, the magic of the mind and the consciousness looking at it. But isn't it, in fact, just measuring it?
Yes.
Thank you. Please explain.
Next question.
No, explain to people, because I'm so tired of talking to hippies.
Joe, you're good.
It just drives me
nuts. You
nuts.
got to carry your people with you.
I try.
Where are they coming from? Where are you pulling? What? Where are you getting your people?
I don't know. Well, I don't own them for sure.
You don't own them.
So they're definitely not my people. They vary greatly. You can't even loop them together.
I know.
If you
have an admirably diverse following, and that not many people can claim that. And it's probably because of your diverse profile. Right? I mean...
Well, I'm as open-minded as I can be.
But on top of that, you're smart
and
you read and you're thoughtful and you're also, on some level, respectful. You'll hear somebody out and you got your MMA thing. So, no, you're in a lot of places and a lot of spaces, and that's a good thing. I mean, we need more unity in this world. So
thank you.
Yeah.
Thank you. So please explain what people are getting wrong.
Okay,
they're very simplistic.
It's much simpler than you think.
Okay.
All right, you ready?
Yes.
So I'm looking at you. The only reason why I can see you is because there's light reflecting off of your face, your body, into my eyes. So there's light. I want to know where you are. So I turn on the lights and I say, there you are. All right. Now, let's make you tinier. Let's make you mini-me, okay, like in the movie.
Right.
So now there's a tiny version of you, a mini-me version of Joe Rogan. Now you're little. I turn on the lights. You're still there. Okay?
Okay.
Because if the lights are not on, I can't see you. I don't know where you are.
Right.
It's that simple.
Okay.
Okay? When you start becoming the size of molecules, right on down to the size of an atom, and I ask the question, where is Joe Rogan the atom? And I turn on the light to see you there, because I think you're there. The photon comes in, hits your atom, and pops you into another location. The very act of trying to measure your position prevents me from measuring your position. And it doesn't have jack shit to do with your consciousness or your mind or your eyes or anything. It has to do with the fact that to know you're there, some information has to come from you to me. Like shining a light on you. And the smaller you are, the more susceptible you are to the energy of the light changing your position in space.
So my question is, how do they know?
You know what it's like? You ever, I don't know if this has still happened, a quarter spills out of your pants pocket on the back seat of a car, and it's there in the wedge between the bottom and the back seat. Mm-hmm. And so you try to reach in to get it, and the act of reaching for the coin makes the coin move farther away from you.
Ah.
The act of reaching for it.
Right, because you're
separated and it just slides down even further. That's not your mind making that happen. It's the act of the measurement that is affecting what it is you're trying to measure. And this was discovered in quantum physics, and to the point where it's the Heisenberg uncertainty principle. It's one of the basic foundations of all of quantum physics.
Okay, so first of all, he talks about the uncertainty principle there at the end, and that's a good opportunity for us to introduce a few concepts that we need to have in order to have this discussion. So the uncertainty principle essentially states that when you're measuring a particle, the momentum and the position of the particle will have a level of uncertainty. In addition, the more you know about one or the other, the less you know about the other. So if you know if you know something about the momentum, you're going to know less about the position and vice versa. So that's the uncertainty principle. And it is not the same thing as the observer effect, as Tyson seemed to be saying there. Those are two entirely separate concepts. The observer effect is just when you take a measurement of something, you are affecting it in the process of measuring it. So if you have a glass of water and you stick a thermometer in the water, the thermometer slightly affects the temperature that you're measuring in a very infinitesimal way. It doesn't really matter to us, though, because of the tolerances that are required in the process of taking a temperature measurement. We can come up with a good number. But I think he's claiming that when you get to the world of the very small, then you are affecting things. Now that can happen. Yes, he is correct. If you shoot a photon at a photon or an electron, you're going to affect it, obviously. But he is wrong about his explanation for the problems regarding quantum mechanics. So a few other things we need to talk about. One concept is quantum entanglement. Quantum entanglement is basically, and I'm just being very, very quick here and a little sloppy, but it is basically, I'll leave information down in the low bar, so please click on the information if you want to learn more. But basically, quantum entanglement involves two particles that are entangled with each other and will have a correlation in their properties. So, for example, if we measure one's spin and it is counterclockwise, if its orbit is counterclockwise, the other one's orbit will then therefore be clockwise. So that's an example of entanglement. Particles are entangled with each other. It's you may recall the spooky action at a distance that Einstein had a problem with. So that's entanglement. Okay, so what they're talking about essentially, and you can hear Rogan, he tried to get to it, but they really didn't talk about exactly what the basis of this part of the discussion was. And it's essentially the double-slit experiment. Essentially, the double-slit experiment reveals that particles like photons and electrons take on both wave characteristics as well as particle characteristics, depending upon the conditions given. What is fascinating is that the conditions given tend to indicate that the act of observing the path of the particle determines the behavior. So this is the basis of what they're talking about. So the basics of the double slit are as follows. A light source, such as a laser, is fired at a screen with a plate placed in between. The plate has two small slits that the laser goes through. What is produced on the screen as a result is not a collection of light in the shape of the slits as might be expected, such as if you have in the world of the very large, a similar setup where you're, say, throwing tennis balls at a screen, and you have this plate in front of it with two open slits that the balls can pass through, and let's say you put paint on them or something, and they're going to mark up the screen, and it's after you just keep throwing tennis balls that have paint on them, they're going to mark up the screen. It's going to have two clumps that sort of represent basically the shape of the slits. Well, you don't get that with this experiment. Essentially what you get is known as the interference pattern. Now, the interference pattern is an indication of wave dynamics. So let's imagine you have a body of water, like a bathtub or something. If you disturb the water in two places and basically the same position, the waves will come out and eventually will interfere with one another. And so what's happening is you get destructive interference And what's produced on the screen are areas where there's light and darkness. And that is the interference pattern. The really fascinating thing about this, though, is that even when one photon is fired at a time at the screen, the same pattern emerges. So that was a very, very disturbing, I guess, aspect of quantum mechanics. If you're firing one photon at a time, how in the world is it interfering with itself? Well, that's what happens. You get the interference pattern. So what happens when we attempt to observe what is happening at the slits and actually see which path the photon took, which slit it went through? When a detector is placed at the slits, the interference pattern disappears and the photons produce a clump pattern on the screen. So this is why some have suggested that our consciousness affects the manifestation of reality, which is the source of Joe Rogan's concern and need to ask the question. So now I want to make it clear that I'm not defending the idea of idealism, nor am I defending the idea of materialism. I'm simply looking at what the science tells us, and Tyson is just wrong as in his explanation, and we'll get to that. So there are two primary interpretations of the results of the Two-Slit experiment. The Copenhagen interpretation states essentially that systems maintain states of superposition, the wave function, until it is measured. So it's essentially a probability wave. And once it is measured, the wave function collapses and the position is determined. Now, the other popular interpretation is the many worlds interpretation. And it states that all states of the particle actually exist in different realms, entirely different, possibly infinite universes. I don't really hold to either of these interpretations, but I'll probably sort of reference the Copenhagen interpretation as I'm speaking, just as sort of to explain things. But I don't necessarily hold to that interpretation. Okay, so how do we know that Neil deGrasse Tyson is incorrect? Well, one of the ways that we know he's incorrect, and the way that I'm going to say that he's incorrect, is the delayed choice quantum eraser experiment. So I'm going to read a little bit from the paper. We can sort of get a little groundwork here in understanding this paper. So the actual mechanisms that enforce complementarity vary from one experimental situation to another. In the two-slit experiment, the common wisdom is that the position-momentum uncertainty relation makes it impossible to determine which slit the photon or electron passes through without at the same time disturbing the photon or electron enough to destroy the interference pattern. However, it has been proven that under certain circumstances, this common interpretation may not be true. In 1982, Scully and Droll found a way around this position momentum uncertainty obstacle and proposed a quantum eraser to obtain which path or particle-like information without scattering or otherwise introducing large uncontrolled phase factors to disturb the interference. To be sure, the interference pattern disappears when which path information is obtained, but it appears when we erase quantum eraser the which path information. Since 1982, quantum eraser behavior has been reported in several experiments. However, the original scheme has not been fully demonstrated. So that's what they aim to do in their paper and doing these experiments. Okay, so just to very quickly go through this and to try to explain this experiment. This is the experimental setup. This diagram represents what happens in the experiment. So let's run through it real quick. As you can see, there's a laser going through a plate with two slits. We have representations of the different paths with red and blue. So after the beam passes through the slits, the photons are shot one at a time again. So after they pass through a slit, they reach a beam splitter, which splits the photons into two entangled photons. As we can see here, that each photon will have 50% of the energy of the original photon. So these green objects here, BS sub A, BS sub B, and BS, are essentially 50% mirrors. So the photons will have a 50% chance of bouncing off of the mirror or going straight through the mirror. So 50% of the time it bounces off, 50% of the time it goes straight through the mirror. That's very important for this experiment to understand what's going on. So now you can see from, thanks a lot, loud car person. You can see from at detector not, you can see from the diagram, the red and the blue, that we won't know the which path information. We won't know which slit the photon went through if it hits detector not. I like just calling it detector not. So the which path information is unknown in every case. Okay, but keep in mind these are entangled photons. Okay, so moving on to D3 and D4, you can see that if it hits detector 3, we know the which path information. We know it's the blue path. If it hits detector 4, we know it's the red path. So the which path information is known when we get a detection at either one of those detectors. So now we move to the really fascinating part of the experiment, and this is the quantum eraser section. So the quantum eraser section, as you can see, this is when the photon passes through the BS sub B or the BS sub A. So what happens, you can see here with the blue path, if it goes, it will reach an actual mirror and bounce off, and if it goes through BS, it'll hit detector 2. So if it then bounces, if it bounces off BS, it will hit detector 1. So you can see that the which path information is erased. We don't know it, whereas we would have known it if it had bounced off BS sub A. And the same scenario is the case for the red path. We're erasing the which path information. When it hits these detectors, we no longer know the which path information. So, detectors 3 and detectors 4, what sort of pattern do you think we will get when we take these measurements? Well, you get a clump pattern. Every single time, you get the clump pattern. Okay? And then what happens when it hits detectors 1 or detectors 2? You get the interference pattern. So this tends to suggest that it's not the act of measuring it that is what's causing these outcomes, but it's just the availability of the information. The very fact that we have access to know the which path is what appears to be causing this. So you can see that in both of these, in any of these cases, we're detecting, we're measuring We're using a device to understand something about the particle. But the measurement isn't causing the collapse. Just measuring it isn't causing the collapse. It's the fact that we know something about that particle. It can know it. The very act of gaining information is what appears to be causing the quote unquote collapse. So what's even weirder about this, and what I didn't say before about detector not, is it's a little closer. It's closer to the beam splitter than the other detectors. So it's going to receive its information before all the other ones do. So the fascinating thing is that anytime you have a detection at this detector, it's always going to do the same thing as its twin. So if it hits detector 3, it's going to be a clump pattern. If it hits detector 1, it's going to be an interference pattern, and so on and so forth. So what this has puzzled many people, what this means is that information appears to be going backwards in time. So, how did the photon know that that its twin was going to be detected at detector 3, for example, and produce a clump pattern, and so therefore it produces a clump pattern? So really weird. I think there are explanations for this involving locality and all of that. I'm not going to go into all that for the purposes of this video. But we know now that you can see, hopefully, that Tyson was incorrect. It's not the act of measuring it that causes the collapse of the probability wave. It appears to be the information being available to us is what is causing the collapse. Really strange. Again, I'm not promoting idealism. I don't think that our consciousness is what's affecting things. But this is the very strange world of quantum mechanics. And it's not so easily explained away, unfortunately. So that brings us to the end of this video. Thank you very much for listening. I'll say as a side note that I'm on Twitter now. I recently started a Twitter account, finally. So if you like what I do, please subscribe to this channel if you haven't subscribed. And please go ahead and follow me on Twitter. Okay, thanks.